In this example, we have a sphere of radius r. It has a mass of m with density linearly changing with the radius such that the density is 0 at the center of the sphere. We're trying to calculate the density as a function of mass. So the first thing I want to do is write down what I'm given. We know that the sphere has a radius of r, so that's the radius. We also know that there is a mass, m, and we also know that density, so density rho, is linearly changing with the radius, so that means rho is dependent upon r, and there is a linear function. So because it is a linear function, it means that we can use rho of r is equal to ar plus b. We don't really want to stick with the a and b convention, so let's change this to rho 1 and this to rho naught. And you'll see why this is useful later on in the course. So let's rewrite this as rho of r is equal to rho naught r plus rho 1. The other thing that we're given is that at the center of the sphere, where r is equal to 0, the density is also equal to 0. So that means rho of 0 is equal to 0. Let's try and combine these two equations to figure out a simplified version for a density function. Rho of 0 is equal to rho naught times 0, oops, not r, plus rho 1. This is 0, 0 plus rho 1, so rho 1 is equal to 0. So now we have a simplified density equation where this is just rho naught times r. Okay, so what are we trying to find? We are trying to find the density as a function of radius. So it seems like we already have our function, but we need to define rho naught. That's the only piece that's missing, and that's what we have to figure out. So let's go through a step-by-step approach as to how we can do that. First, the only thing that we're given is radius and mass. So it seems like we're going to have to relate density to mass and radius r, or something along those lines. So first of all, we know that density is equal to mass over volume, which means that mass is equal to rho times v. In order to get to capital M, I'm going to have to find the total mass. So this rho of r is dependent upon r, whereas each individual element of M will have a corresponding volume element as well. So what we're trying to find here is find the differential mass element, and that is called dm. So if we take a look at this equation again, we have m equals to rho times v. If we're looking at each individual differential element, that means we have a tiny step or a tiny mass. We know that the density is going to be a function of r, so we can't change that. And for that tiny mass, we also have a corresponding volume element. This volume element, we can actually, we've already done this before. It is, for a sphere, it's r squared sine theta, dr, d theta, d phi. So that means I can write my differential mass element as rho of r squared, sine theta, dr, d theta, d phi. We also know that rho of r is equal to rho naught times r. So we can simplify this even more. Like that. After that, we can solve for m using the integral of dm. So m is equal to the integral of dm, which can be rewritten as the integral of rho naught r cubed sine theta dr d theta d phi. So it's no longer one integral, it's actually three integrals, because dm is defined by three different differential elements. In order to solve this, I'm going to have to figure out my bounds. First, I can take out this, but I'm going to have to determine what my boundaries are in order to continue. So we have three variables to look at: r, theta, and phi. R goes from 0 to capital R, the radius of the sphere. Theta goes from 0 to pi, like our spherical coordinates. And then phi goes from 0 to 2 pi. So all of these boundaries are constants, which means that none of them are dependent upon one another. Because of this, I can separate, I can choose whatever order I want for integration. So now I have 0 to r, and then 0 to pi, and then 0 to 2 pi of r cubed sine theta. This was d phi, d theta, dr. To make my life easier, I want to look at this function as well to see if I can separate it into a product of just solely individual variables. So I can. This is just r cubed times sine of theta. That means I can have three individual integrals instead of a triple integral to solve inside out. So this is rho naught. We have the integral from 0 to r of r cubed dr, integral from 0 to pi of sine theta d theta, and the integral from 0 to 2 pi of d phi. This gives us rho naught integral from, we have r to the 4 over 4 from 0 to capital R. We have negative cosine theta being the integral of sine theta from 0 to pi, and we have phi from 0 to 2 pi. M is now equal to rho naught, capital R to the 4 over 4, minus cosine of pi, plus cosine of 0, and 2 pi. This is simply cosine of pi is negative 1, so this is 1. And cosine of 0 is 1, so we actually have 2 there. So we have 2 times 2, let's just rewrite this. We have rho naught r to the 4 over 4 times 4 pi. The 4's can cancel out, and we are left with pi rho naught r to the 4. Okay, so we figured out an expression for capital M, but that's not exactly what we're looking for. We're trying to define the density function, and our goal was to try and solve for rho naught, which we can now. We have rho naught is equal to m over pi r to the 4, and because rho of r is equal to rho naught r, we can rewrite this as rho of r is equal to rm over pi capital R to the 4. And now we're finished with the question. In this example, the density of a sphere varies as rho equals to rho naught sine theta, and we're trying to calculate the total mass. So first things first, write down what we're given. We have a sphere. We know that it has a density that's dependent upon theta, and that's rho naught sine theta. And we're trying to find capital M, the total mass. Now let's start with our approach. We know that we should find in order to find the total mass, we're going to have to integrate the differential mass element. So we know that to find M, we need dm. So that's going to be our first step. From the previous problem, we knew that dm is equal to rho dv, and rho is dependent on theta, so we have to input that as well. Because this is a sphere, we have dv being equal to r squared sine theta, dr d theta d phi. That means dm is equal to, we know that this is rho naught sine theta, and this is r squared sine theta dr d theta d phi. Okay, so I guess we can simplify this a little bit more. We have r squared sine squared theta dr d theta d phi. Next, we should integrate, find the total mass using the integral of dm. So that means m is equal to the integral of dm, which we've redefined as 3 different differential elements. So that means we have to have a triple integral of rho naught r squared sine squared theta dr d theta d phi. I can't proceed without any boundaries, so I'm going to have to find the boundaries here. For a sphere, we have r, theta, and phi, just like before. So for spherical coordinates, this would be 0 to capital R. For a full sphere, this is 0 to pi, and this is 0 to 2 pi. Once again, these are all constants. None of the variables, none of the boundaries and the variables are dependent on one another, so it doesn't matter what the order of integration is. I'm just going to go from top to bottom. So 0 to r. The other thing, before we even write this out, maybe we should take a look at the function first. So over here, oops, went too far. To save a step, we can factor out rho naught, and then I can take a look at whatever's left. So I know that r squared can be separated, and sine squared theta can also be separated. And that means I can have 3 separate integrals instead of a triple integral. So we have the integral from 0 to r of r squared dr, so that's all of the r related terms. We have the integral from 0 to pi of sine squared theta d theta, and the integral from 0 to 2 pi of d phi. Now m is going to be equal to rho naught. This is r cubed over 3 from 0 to r. And then we have the integral of sine squared theta d theta. That's not something I want to solve directly. You would have to use a trig identity. You'd have to use the half angle formula to rewrite it, and then use substitution to solve for this. So we're just going to quickly go back to our visualization of functions chapter, and let's just try to graph this and see if we can solve this visually. So let's say, as an aside, we want to solve for the integral from 0 to pi of sine squared theta d theta. And the first thing we can do is separate one of the sine. Oops, I'll separate one of the sine. I thought it was sine cubed, but it's not. So we have this. Let's graph this. We have theta and y, and this is 0. So if you don't know what sine squared theta looks like, let's just start with sine theta and transform it. So for sine theta, let's just make this bigger. So something like this. This is 1 and this is -1. We also know that this is pi and this is 2 pi. So the middle points are pi over 2 and 3 pi over 2. If we're squaring this, it means that 1 squared is still going to remain as 1. 0 squared is going to still be 0. And -1 squared becomes 1. Because all of these values are less than 1, when you square them, they're going to be smaller than they were before. So that means we're just going to have something like this. Can't really draw it right. Like that. And the integral is telling us to solve for the area underneath the curve from 0 to pi. So that means I want the area for just this bump. And what I can do is cut this in half. And if I take a look at the right side, maybe I can flip it over and put it here so that it matches perfectly. This should give me some sort of like that. So this was the blue area and this is the red area. We know that the length here is pi over 2, and we know that the height is 1. So the total area is just pi over 2 times 1. So if you know your trig functions and you know how to visualize the curves, then it becomes a really handy tool so that you don't have to go through so much brute force math just to figure out an integral like this. So we know that this is equal to pi over 2. That means I'm just going to plug this in, pi over 2. This is phi from 0 to 2 pi. M is equal to rho naught pi over 2. And then we have r cubed over 3 times 2 pi minus 0. We can cancel out the 2's. We end up with a pi squared, so we have 1 over 3 rho naught pi squared r cubed. In this example, the density of a sphere is uniform and given by rho equals rho naught. Our job is to calculate the total mass. So let's just write down what we're given again. We have a sphere. So all of these are starting to look familiar. We have rho equals to rho naught for uniform density. And we're trying to find the total mass again. So capital M, total mass. Now the approach, pretty much the same as before. In order to find M, we need the differential mass element, dm. We know that dm is equal to rho dv. We know that rho is always rho naught because of the uniform density. And we also know that dv is equal to r squared sine theta dr d theta d phi. Okay, so this is starting to get look familiar. So why don't we solve for capital M using the integral of dm. And I'm going to do this a bit differently because there is a neat trick that you can use because this is uniform density. So if I have capital M being equal to the integral of dm, this is another way to write dm. So I have the integral of rho naught dv, which is equal to rho naught times the integral of dv. The integral of the differential volume element is simply the volume of the object you're looking at. So over here, this is the volume of the sphere, which is equal to 4 over 3 pi capital R cubed. So this saves us so much time so that we don't have to do a triple integral and then set the boundaries and everything. We know that we have the integral of dv, so we have capital M being equal to rho naught times 4 over 3 pi r cubed. We're going to put that all together and we get 4 over 3 pi rho naught r cubed as our answer. So obviously this is much shorter and much easier, so keep in mind the more practice problems you do, the more trends you're going to see, just like we've noticed over here. So keep practicing so that you can spend your time wisely. In this example, we're trying to calculate the moment of inertia of a sphere of mass m and radius r rotating about the axis shown in the figure below. The sphere also has uniform density. So this is a much more complicated problem, it seems. We're now not looking at trying to find the total mass. We're trying to find the total moment of inertia of a sphere. So let's write down what we're given. We know that we're looking at a sphere. We know that we have mass m as the total mass. We know that we have capital R as the radius. And we know it's spinning around an axis. So why don't we go ahead and call this axis the z-axis for convenience. The z-axis doesn't always have to point up. Any coordinate system can be rotated just so that we can do our math a lot easier. So now what we'd want to do is, what else do we have? The sphere has uniform density, so we know that rho is going to be equal to rho naught. And I think that's it. We're trying to find the moment of inertia. Keep in mind, capital I is going to be used for the total moment of inertia. So on the topic of moments of inertia, what is the equation that we use for it? We know that from ECE 105, so from ECE 105 and potentially other physics or calculus courses, dI is equal to some sort of mr squared, or usually it was dm r squared. And then we would have to integrate that to get I, and that's equal to this. So at least we know what we're trying to find now, and the starting point is to get that dI set up properly. So let's start with our approach. We need to find an expression for dI. We know that dI is equal to dm r squared, but we have to keep in mind how r is defined. R is the distance that dm is away from the axis of rotation. So if our axis of rotation was z over here, and we have our sphere, let's consider a point A. Let's just draw the center of the circle first and call this O. Let's say there's some sort of a distance away from the origin, and it makes an angle of theta with the z-axis. This r is the distance that this mass, so this dm, this point A is going to have some sort of small differential mass element, and that is going to be a distance away from the z-axis, and this distance is r sine theta. So it's important to realize what this r means, and that means r is equal to r sine theta in this case. So we have dI is equal to dm r sine theta squared. Kind of running out of space. So dI equals to dm r sine theta squared. So next, let's solve for I using I equals to the integral of dI. And that means we have the integral of r sine theta squared dm. So looks like a simple integral. I just don't have dm yet, so we're going to have to solve for that. We're going to find dm. We already know that dm is going to be equal to some sort of rho dv, but we have uniform density, so rho is simply equal to rho naught, so due to uniform density. So we have dm equals to rho naught dv. Apart from that, we also know that dv is equal to r squared sine theta dr d theta d phi. What else do we know? We know that because of uniform density, rho naught is simply going to be the same everywhere, no matter what dm you're looking at. So the total mass divided by the total volume of the sphere is going to give us our density. So total mass divided by volume of a sphere, 4/3 pi capital R cubed, which is equal to 3m/4 pi capital R cubed. So now we have a whole bunch of additional information that we can add to this. So we have the integral of r sine theta dm. dm is now going to be defined by 3 differential elements, so we do need a triple integral at this point. So then we would have r squared sine squared theta, and we have rho naught, which is running out of space. I still have to add the dv in, so r squared sine theta dr d phi d theta. Okay. So why don't we try and simplify this a little bit more? Let's pull out all of the constants. So we have 3m/4 pi r cubed, and then the triple integral of r to the 4 sine cubed theta dr d theta d phi. Okay, so now we have to look at our bounds in order to integrate this. For a sphere, we have r, theta, and phi. We know r goes from 0 to capital R, theta goes from 0 to pi, phi goes from 0 to 2 pi. So looking at this, I know that I can separate this into r to the 4 and sine cubed theta, which means I can create 3 separate integrals. The integral from 0 to r of r to the 4 dr, the integral from 0 to pi of sine cubed theta d theta, and the integral from 0 to 2 pi of d phi. Now I have I is equal to 3m/4 pi r cubed. This will be r to the 5/5 from 0 to r. We're going to take a look at this. So we're going to go to an aside and try and figure out the integral from 0 to pi of sine cubed theta d theta. So I don't really want to do this graphically just because I don't want to graph sine cubed theta, but what I can do is try and rewrite it. So 0 to pi of sine theta sine squared theta d theta. That means this is equal to the integral from 0 to pi of sine theta. I can rewrite sine squared theta as 1 minus cos squared theta d theta. And now I can use substitution. So we're going to let u equal to cosine of theta, which means du is equal to negative sine of theta d theta. One thing about this, I can use this to replace sine theta d theta. So that would simply be negative du equals to sine theta d theta. We have exactly this over here. So we're going to replace everything underlined in green by negative du. Afterwards, we have 1 minus cos squared theta, but cos theta is equal to u, so we have 1 minus u squared. The last thing that we haven't looked at are these bounds. So because I'm changing a variable, I have to change the bounds as well. So u of 0 equals to cosine of 0 equals to 1. U of pi is equal to cosine of pi, which is equal to -1. So I gotta change the boundaries as well. This means I have the integral from 1 to -1 of 1 minus u squared times negative du. I might as well switch this to u squared minus 1 du. We can distribute these, so we have 1 to -1 u squared du minus the integral from 1 to -1 of du. That gives me u cubed over 3 from 1 to -1 minus u from 1 to -1. This gives me -1 over 3 minus 1 over 3 minus -1 minus 1. That would be -2 over 3 minus -2, which is +2. And that gives me -2 over 3 plus 6 over 3. That is 4 over 3. So now I can put 4 over 3 here, and then I have phi going from 0 to 2 pi. Let's try and simplify it as we go along. The 3 cancels out, the 4 cancels out. Say I is equal to m over pi r cubed, r to the 5 over 5, and 2 pi. So anything else to cancel, we have the pi, and we have the r cubed, which turns this into r squared. So I is equal to 2 over 5 mr squared as the total moment of inertia of a sphere. So let's take a look at this problem. It's quite different. We're looking at an Archimedes spiral, which is the trajectory of a point moving uniformly on a straight line of a plane, while the line itself turns uniformly around one of its points. An example is the rotation of the stylus on a good old vinyl disc. The curve of one type of an Archimedes spiral is going to be given by the mathematical function r equals e to the power of phi, where r is the radius from the origin and phi is the angle that the line makes with the x-axis. So this exercise is this example is going to get us to calculate the following parameters for one full turn of Archimedes spiral. So basically that means your phi is going to change from 0 to 2 pi. So we're being asked to figure out the circumference of the curve and the area enclosed within the curve. So before I move on, it might be beneficial for us to actually picture what an Archimedes spiral looks like. So we have our x-axis and our y-axis, and this is the origin. We'll call this O. The assumption is that we start here, right at the origin, and we're going to start at an angle of 0. So this is when phi is equal to 0, and we're going to do a full rotation around to reach 2 pi. It's also saying that the distance r from the origin is going to increase linearly as we go around the coordinate system. So starting here, we have 0. Then as we turn around, we get a larger and larger radius. Something like that. And so in part 1, we're trying to find the circumference. And in part 2, we're going to try and find the area enclosed by the curve. So in terms of the approach, let's quickly just think about how we would go about solving this. For the circumference in blue, it makes sense that we're going to break up the path taken into tiny little pieces. So could make sense that we consider this a differential length element. And that means it's going to, let's draw this a bit better, it's going to form a wedge. So by being able to determine this, we should be able to figure out what DL is and then just add up a whole bunch of DLs to get our total path taken, or the total circumference. So that seems to be a good approach for number one. For number two, the area enclosed, what if we just split this up into pieces like this, and then carry on until we get the total area of the curve. So every single time we're just going to move by d phi. And of course the radius is going to change too for each of these. So we seem to have a general approach to both of these problems. Now we're going to go tackle each one separately. So number one, we want to figure out the circumference. Okay, so let's just draw this wedge again in blue. And let's just, not in blue, let's draw the spiral. We have a starting point and an end point, like that. I had mentioned that we should probably take a look at some distance here as DL. I'm just going to make DL bigger for the purposes of a drawing. So we have DL like this, and it means that I have a radius here, which gets spun around in a circle like this around the origin O. And this is also R, but we have d phi. So we have a change in phi. Apart from that, there's this piece that's missing over here, and that is going to be in blue. I'm going to draw this a little bit thicker. That is going to be the change in radius. So we have d phi and dr, and the last thing I haven't labeled is right here in green, which is r d phi from our polar coordinates. So looking at the unit vectors, let's label this. We know r is changing radially outwards, so that means we have a unit vector of r hat going this way. It's pointing radially outwards. We have dl, which is simply going to be tangential, just like we've drawn it, so it'd be something like this, or like that. The last one we have is r d phi, so it means that we have some sort of tangential component here as well, and this is phi hat. Okay, so let's try and ask ourselves, how do we define dl. We must relate it to dr and d phi somehow. So from the diagram, what we see is that so from the diagram, we see that this can be vector addition. So we have r d phi going this way, and then we have dr going this way. So vector tail to tip addition. We then have dl going this way as the resultant. So that means dl is simply going to be r d theta of phi in the phi hat direction plus dr, and dr is going to be in the r hat direction. And that's pretty much it. We now have to figure out a magnitude for the vector dl, and in order to get that magnitude, remember from our dot product lesson, we can multiply the vector by itself so that we can get the magnitude squared. It's also distributive, so we now have to have r d theta we have r d phi hat plus dr r hat dotted with itself. So we have r d phi hat plus dr r hat. This is going to give us dl squared. So then we have, let's just make this a little bit clearer so we don't get confused. This is dl squared. This will be r d phi squared phi hat dotted with phi hat plus 2 r d phi dr phi hat dotted with r hat plus dr squared r hat dotted with r hat. Okay, there is a lot. Now we have dl squared. Before we go and solve anything, let's take a look at these unit vectors that are dotted with each other. Unit vectors have a length of 1, so if they're dotted with each other, it'll simply be 1 times 1 times cosine of the angle between them. So if we're dotting the same unit vector, we only care about the angle between them, which is 0. Cosine of 0 is 1, so this is simply 1. Same as this. With phi and r, we take a look at the two of them here, phi and r. They are perpendicular to each other, so 90 degrees, and the cosine of 90 degrees is 0, so this whole term simply goes to 0. So we can simplify this and have dl squared is equal to r d phi squared plus dr squared. So dl can be expressed as r d phi squared plus dr squared. So that's we're taking the square root of that to get to dl. Well, one of the things we do care about is trying to find the circumference. And in order to find the circumference, we're going to have to integrate with respect to phi. So I need to be able to take d phi out of this square root function. So why don't we try and do that? We have dl, so I'll just say here, must take out d phi so that we can integrate with respect to it. If we take out a d phi, it means we are left with r, we have d phi squared, then we're left with r squared plus dr over d phi squared. Now we can take it out. We have dl is equal to d phi times the square root of r squared plus dr over d phi squared. Okay, we're getting a little bit closer, but there's still one missing thing. I can't have d phi and dr and be able to integrate with respect to just phi to get my circumference. I need to be able to replace r with the function I was given. So we know that r was equal to e to the power of phi, and we also know that dr over d phi is equal to e to the power of phi as well. So dl is equal to d phi times the square root of r is equal to e to the phi, so squared it would be e to the 2 phi plus e to the phi squared, which is e to the 2 phi. dl is equal to d phi times 2e to the 2 phi. dl is equal to the square root of 2, and the square root of e to the 2 phi is going to be simply e to the phi d phi. Okay, so with this, we can now calculate, find the circumference, c, by integrating dl for phi going from 0 to 2 pi. So c is equal to the integral of dl, which is equal to the integral from 0 to 2 pi of the square root of 2 e to the phi d phi. C is equal to, take out the constant, we are left with e to the phi from 0 to 2 pi. Oops, don't need that anymore. C is equal to the square root of 2 e to the 2 pi minus e to the 0, which is 1. And now we have our answer for the circumference of the Archimedes spiral for one rotation. Number 2, we wanted to figure out the area enclosed by one rotation of the Archimedes spiral. So in this case, before we were trying to figure out circumference, so we needed a differential length element. We're trying to find the area now, so we need to find a differential area element, which we usually call ds. And because we're working in polar coordinates, we've defined ds before. ds, remember, was equal to r dr d phi. We now know that r is equal to e to the phi. And we know that, what else? The range of r is going to go from 0 for the minimal distance, going towards whatever it's dependent on, so e to the phi will be its max. So that means I can just solve for a by integrating with respect to ds. We have a is equal to the integral of ds, which is equal to the double integral of r dr d phi. So what we want to do now, we already have the boundaries for r. We do know that the boundary for phi, I forgot this, is 0 to 2 pi. So a is going to be the integral from which one first? We know that r is dependent on e to the phi, so our boundary condition for r is going to be dependent on something, so it has to be integrated first, which means phi is going to be the outermost integral. Then we have 0 to e to the phi, and this would be r dr d phi. So a is equal to, obviously we can't separate this because r is dependent upon phi, and so is the answer. We have integral from 0 to 2 pi, so r squared over 2 from 0 to e to the phi d phi. A is equal to 1 over 2. I can take out the integral from 0 to 2 pi. So I'm left with r squared, which means I have e to the 2 phi minus 0 squared, like this. A is equal to 1 over 2, and I have the integral of e to the 2 squared. If I integrate e, if I derive e to the 2 phi, I actually get 2e to the 2 phi, so I have to divide by 2 to get rid of that extra 2. And this is from 0 to 2 pi. Now a is equal to 1 over 4, and we have e to the 2 times 2 pi, so e to the 4 pi minus e to the 0, which is 1. So just by going through these two exercises, we've been able to figure out the circumference and the area enclosed of one full rotation of Archimedes' spiral. There are some important integrals that we'd like you to know about moving forward, specifically these two, and they have to do with the integrals of sine functions. So number one, it's if you have the integral from a to b of sine squared theta d theta, or the integral from a to b of cos squared theta d theta. So if b minus a is equal to some integer multiple of pi, so where m is an integer, the integral is always going to be m times pi over 2. So that's a shortcut if you want to memorize it. If you want to understand it, you can do so too, just by integrating between different boundaries and looking at the shape of the curve. Number two, if you have the integral from a to b of sine theta cos theta d theta, using the same comparison, if b minus a is equal to m times pi, where m is also an integer, then the integral is always 0.